In this video, we're going to look at ways to measure batting performance. Batting performance is a bit tricky to measure because, with the exception of home runs, one needs the assistance of teammates to score a run. You need to have teammates get on base who are then advanced when you are at the plate. What we are going to do is to use teams as the unit of analysis rather than individuals. So all of the at-bats that a team accrues, all of the hits, all the home runs, all of the stolen bases and so forth can be all put together, and we're going to look at the team scoring. We're going to evaluate the team's batting performance, and we will develop some metrics to allow us to do that, and we can then apply those metrics to individuals. We're going to need several packages in this particular tutorial. Two of them you may not have already. So if you haven't installed Sean Lehman's package of Major League Baseball data, you should do that with the top command. And you should also install the second package called galley, and it does not have an E, so it's galley, it's spelled correctly there. So install those packages if you haven't, and then we're going to load 4 different packages, Lehman and galley, and also dplyr and ggplot2, which we've used a lot in previous videos. So we'll run that, and we're going to be looking at the teams data frame, the structure of teams. We can see we have a number of different columns, but we're only interested in a subset of them. So what I will do is to use dplyr to only choose the columns that I am interested in. So I'm going to make a new data frame. I'm just going to call it df, and it's going to be based on the team's data frame. I'll give my piping operator, and now I'm going to select. And in this case, it's easier for me to select by removing columns rather than by specifying columns. So what I'm going to do is to subtract or exclude all the columns from franchise ID, all the way over to World Series wins. You can see that right here. And I will also get rid of all the columns that go from starting with runs allowed to the very end of the data frame, and the last column is called Team ID Retro. Now if I take a look at the head of my data frame, I will see that I have 15 columns. You can see that those are indicated up here. What I also want to do is to restrict my analysis to a subset of all of the years in the data frame. So we'll use the filter command and string that together with the piping operator. So I'm just going to look at the first decade of the 21st century. So we'll have year ID greater than 1999 and year ID less than 2010. So we'll look at the 10 years between 2000 and 2009. And I know from having done this analysis earlier that there are some missing values for the caught stealing column, and they will of course cause problems when we're trying to summarize data. So I'm going to go ahead and issue a command now to remove any row that has a missing value for caught stealing. So I've entered that there, and we'll run this code. And now you can see that I have 300 observations in my data frame, which correspond to the 15 teams in each league, 30 teams altogether in the 10 years. And I've got my 15 different columns, 15 different variables. So now what I want to do is to create some new variables that are the metrics that I want to test to see how good they predict runs. So we'll again add a piping operator. This time I'm going to use the mutate command, and preparatory to developing some of these metrics, I need to calculate a few preliminary metrics. So one that I'm going to need is plate appearances, which is not given in the layman database. So I'll need to create that myself. Some PA is simply going to be equal to at bats plus bases on balls plus hit by pitch plus sacrifice flies. So I have that, and put a comma there and go to my next line. And I'm also going to need to calculate the number of singles. You can see that I've got the number of hits, and I've got the number of doubles, triples, and home runs, but I don't have a separate column for singles. So I'm just going to call the singles 1xb's, and they're going to be equal to the hits minus the doubles minus triples minus home runs. So I've got that, and I need one more variable, and that's going to be total bases. So now that I have singles, I can calculate that easily enough. So we'll call that TB, and that's simply going to be equal to the number of singles plus 2 times the number of doubles plus 3 times the number of triples plus 4 times the number of home runs. So I'll run this code now, and I have my new data frame that now has 18 variables, as you can see up here in the global environment. And if I look at the head of my data frame, then I have my 3 new columns: plate appearances, singles, and total bases. We'll start with a traditional measure of batting performance, and that's simply batting average. So we'll say batting average simply equals hits divided by at bats. So run this line again, and you note that batting average is given to 7 decimal places. So what I'd like to do is to round batting average to 3 numbers to the right of the decimal place. So I'll use the round function here to do that, and I specify that I want to do it 3. And so now I'll just run this, and again we'll look at the head, and now I have more familiar looking batting average. Well, what I'm going to do now is to just paste in the remaining metrics that I want to measure. And we'll go through them individually. Batting average we've already done. On base percentage, and again I'm rounding to produce it in a familiar form with 3 spaces to the right of the decimal. So on base percentage is simply the number of hits plus walks plus hit by pitches divided by plate appearances. Slugging is the total bases divided by at bats. OPS is OBP added to SLG, which is really a fairly peculiar metric. It's highly artificial because we're adding essentially apples and oranges. We're adding on-base percentage, which is the proportion of plate appearances during which the batter gets on base, to a metric that's not really a percentage at all, slugging. It's a number that varies between 0 and 4, and it simply gives the number of total bases per at bat. So it can vary between 0 and 4. We have isolated power, which separates out singles from extra base hits. So a double counts for 1 extra base, a triple counts for 2 extra bases, and a home run counts for 3. Singles count for no extra bases, so they don't enter into the isolated power calculation. So what we have with runs created is a measure developed by Bill James, and it consists really of 3 terms. This first term here is a measure of getting on base. The second measure with total bases and stolen bases is a measure of advancing runners, either yourself or our teammates, and then we divide through by at bats and base on balls, so that represents the number of opportunities. So that's a different metric. We also have a metric called batting run average, which is equal to the product of OBP and slugging. And finally, we have two other measures. One is strikeout rate, so it's simply the number of strikeouts per plate appearance, and the base on ball rate or walk rate, just simply the number of walks divided by the plate appearances. So let's run all of this code. So we have these various metrics, and we want to see how well they can predict runs. But let's take a quick look at the structure of our new data frame. And I don't really need all of these columns here. I only want to use some of them to use to predict runs. So I'm going to take a subset of my original data frame, and I'll just call it DF1. So I'm going to take the original DF, and I'm going to select only a portion of the column. So I obviously want runs, and then I also want to have my batting average, OBP, slugging, OPS, ISO, RC, BRA, strikeout rate, base on ball rate. So I've got all of those columns there. So I'll run this, and I've got DF1 up here with my 10 different variables. It's often useful to take a look at the relationship between two variables graphically. So what we can do is to use a command that's available in base R, it's simply called the pairs command. So we'll simply feed all the information that we have so far here into pairs, and what R will do is to prepare a whole bunch of scatter plots. This particular type of scatter plot is called a SPLOM, which stands for scatter plot of a matrix. So the matrix would be the 10 by 10 matrix that we have here of all these different metrics that we have. And of course, what we're interested in is how well these various metrics correlate with runs. And so we can see that batting average is fairly sloppy, that on-base percentage is a little better, slugging is maybe marginally better, OPS is better yet, a much tighter fit there, isolated power, fairly sloppy, runs created looks very tight, and batting run average looks very good as well, and strikeout rate and walk rate seem to have very little effect. So it's a nice way to take a quick look at your data. And obviously what we probably want to do is to not worry so much about examining how well strikeout rate and walk rate can predict runs, but we'll concentrate on some of these other ones. But there are other ways to look at your data using a SPLOM, and having loaded galley, we can use a command in galley called ggpairs. Let's zoom in on it. And you can see that it provides a scatter plot in the lower left of the diagram for each of those 10 metrics that we have. Along the major diagonal, we have a density function for each of those variables. And then we get the correlation coefficients for each of the pairs. So as an example, if we are looking at the correlation coefficient between batting average and runs, it's equal to 0.785, which is not bad, but it's not as good as OBP 878 or slugging 897, and even better yet, OPS 0.947. Isolated power is relatively poor. Runs created is better yet, and batting run average is pretty good. And you can see that strikeout rate and walk rate are fairly poorly correlated. What we'd like to do now is to actually explore the relationship between runs and the metrics that look like they're maybe the best fit. So what we want to do now is to use a linear regression. So what we're going to do is to establish regression analyses for 5 of the best fits. So I'll call my first one mod OBP, model OBP, and it's simply going to be equal to the linear model. We call that, and we're going to regress runs by OBP, and I need to give my data frame. So I'll just use DF here actually. And if I call mod OBP, then I get my intercept and my slope. Really more interested in the information that's bound up in the summary. So let's take a look at that. So what we see here is that the slope is highly significant. So we have a highly significant slope. The p-value is less than 0.001. We can also look at the multiple r squared. So that's the r value that we saw earlier squared. And this tells us that 77% of the variation in runs can be explained by knowing the on-base percentage. Another way of measuring the effectiveness of on-base percentage and explaining run variation is to look at the size of the residual standard error. So here you can see it's 37, and we want to keep that in mind as we look at other regressions. So I'm going to go back up here, and just to save a little time, I'm going to copy this 4 more times. So we're going to do slugging. So that's, in this case we do that, and we'll do OPS. And we'll do runs created. We'll do batting run average. And let's do one more. Let's just do the traditional batting average. So I'll run all 5 of these new regressions. And we can take a look at each of them in turn. We'll just look at the summaries of them. So if we look at the summary of slugging, then we see that our multiple r squared is a little bit better. It's 80.44%, and our residual error is a little lower, 34 from 38. So let's take a look at OPS. And my r squared is even better yet, almost 90%, and my residual error is down to 25. So that looks like a very good candidate for a good measure of batting performance. Runs created, even better yet, my r square value is over 0.9, and my residual standard error is a little bit lower as well. Summary of BRA. Also very good, over 0.9, and the residual standard error is very low as well. And then we'll look at the more traditional batting average. And we can see there that the fit is relatively poor, that I've got almost twice the amount of residual standard error that I do with my best fits of BRA and RC, and the multiple r squared is 0.61 or 0.62, which tells us that 38% of the uncertainty in runs cannot be explained by knowing what the batting average is. So there's a lot of unexplained error when you simply use batting average. Of course, anytime we do a regression analysis, we want to make sure that we haven't violated the assumptions of that regression analysis. So since RC was one of the best measures we have, let's just test our regression there. So what we'll do is to use the plot command, and we're going to first ask if the errors, the residuals, are randomly distributed. So this plot should look like the night sky. The points should be randomly scattered all around the Cartesian coordinate space here. And we can see that that's true. We have high values at the higher end of the distribution of fitted values, and we have high and low values lower end and high and low values right in the middle. So we can feel pretty good that we haven't violated the assumption of randomly distributed residuals. We also need to know that the residuals have a normal distribution, and we can test that very easily just by looking at a QQ plot. And if the data, if the residuals are normally distributed, then these points should fall pretty much on this little dotted line that you see there, and that in fact is the case. So we have checked two of the most important assumptions of a regression analysis, and we find that we get just what we want. Finally, we can use ggplot to prepare a scatter plot of runs against runs created as an example. So I've already written the code, and I just paste that in here. So we'll take a look. And for our 300 data points that we have, it's a pretty nice fit. And you can see, zoom in on this a little bit. You can see there's a 95% confidence interval around the regression line, and the error around the line is virtually nil in the middle of the distribution when RC values are between 700 and 900. As you get higher and lower, then, as is typical, the confidence intervals increase a little bit, but that's still a very tight fit for this particular relationship, and you can see that there aren't many points that are very far off of the predicted line. So our procedure then has been to use teams, offensive statistics, to develop a team metric to explain how many runs get scored by that particular team. And then what we will do now is to take that metric and apply it to individual players. And what we can see is that the traditional use of batting average to evaluate batter performance is a much weaker metric than a lot of the more modern metrics. And the ones that I've shown you here are not an exhaustive list. So Baseball Prospectus has a metric they call true average, and Fangraphs has a metric they call weighted on base average, both of which take into account park effects and the era in which a baseball player played and so forth. So there are a number of other candidates for measuring batter performance that you can investigate as well.